Good morning students. Myself Vaidehi working as assistant professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject CEC 334 Analog IC Design for 6th semester ECE students. Today the topic is from the Unit 2 High Frequency Amplifier and Characteristics of Noise Amplifiers. In this lecture, we will discuss three important concepts in analog circuit design: the Miller effect, association of poles with the circuit nodes, and their impact on amplifier frequency response and noise performance. These concepts are essential because they determine the bandwidth, stability, and high frequency behavior of amplifiers using an analog and RF systems. First, we see about what is the Miller effect. The Miller effect was first described by John Milton Miller in 1990. It explains how a small capacitance connected between the input and output terminals of an inverting amplifier appears much greater when viewed from the input side. The effective Miller capacitance is given by Cm is equal to C into 1 plus AV into C underscore M is equal to CV of 1 plus AV Cm. Here C is the feedback capacitance and AV is the voltage gain of the amplifier. As the gain increases, the effective input capacitance increases significantly, reducing the amplifier's ability to operate at high frequencies. Next we see the visualizing the Miller effect in a common emitter amplifier. To understand the Miller effect, consider a common emitter amplifier. A small collector to base capacitance exists naturally inside the transistor. This capacitance is referred as CCB. Because the amplifier provides voltage gain, this capacitance appears multiplied at the input. As a result, the input sees not only the base emitter capacitance but also a much larger effective capacitance due to Miller multiplication. This increased capacitance slows down the amplifier's response and reduces its bandwidth. Next we see about the Miller effect impact on frequency response. Miller effect has major influence on frequency response. As frequency increases, the large effective input capacitance presents a lower reactance, causing signal attenuation. This leads to gain roll-off at high frequencies. For example, a feedback capacitance of only 1 picofarad combined with a gain of minus 60 can dramatically reduce bandwidth. The Miller effect also affects switching speed in high-speed analog circuits and power electronic converters. Therefore, controlling the Miller effect is a key design objective. Next we see about the mitigating the Miller effect. Several techniques are available to reduce the Miller effect. One common approach is the use of cascade amplifier stages. A cascade arrangement reduces the voltage variation across the feedback capacitance, thereby minimizing Miller capacitor multiplication. Another technique is designing circuits with a low output impedance, allowing parasitic capacitances to charge and discharge more quickly. Engineers also use neutralization and compensation methods to cancel unwanted feedback effects. These techniques help improve bandwidth and high frequency performance. Next we see about the association of poles with nodes. Now let us discuss about poles and nodes. Every node in an amplifier contains some resistance and capacitance. Together these elements form an RC network that introduces a pole into the frequency response. A pole represents a frequency at which amplifier gain begins to decrease. The pole occurring at the lowest frequency is called the dominant pole because it primarily determines the amplifier bandwidth. The Miller effect often shifts this dominant pole to an even lower frequency by increasing the effective capacitance at the input node. Therefore, identifying poles associated with each node is important when designing stable amplifiers. Next we see about the pole splitting and the Miller compensation. In multi-stage amplifiers, compensation techniques are often required to maintain stability. A common approach is Miller compensation. A compensation capacitor is connected between amplifier stages. This capacitor causes pole splitting. The dominant pole moves to a lower frequency, while higher frequency poles move further away. This separation improves phase margin and prevents oscillations. As a result, the amplifier remains stable even when operating with high gain. Next we see about the noise characteristics in high frequency amplifiers. Besides frequency response, noise is another important concern. Thermal noise is generated by resistive components and increases with temperature. Short noise results from the random movement of charge carriers across semiconductor junctions. Flicker noise dominates at low frequencies and originates from imperfections in semiconductor materials. Miller effect can worsen noise performance because it increases the effective input capacitance and broadens the noise bandwidth. Consequently, the signal to noise ratio may degrade at high frequencies. Proper circuit layout, shielding, and component selection are essential for minimizing noise. Next we see one practical example for high frequency amplifier design. In RF amplifiers, cascade configurations are frequently used because they suppress the Miller effect and achieve bandwidths greater than 1 GHz. In operational amplifiers, Miller compensation is commonly employed to balance gain, bandwidth, and stability. Designers must always consider trade-offs. Increasing gain may reduce bandwidth, improving bandwidth may increase power consumption. Reducing noise may require additional circuitry. Therefore, amplifier design involves balancing multiple performance parameters. Finally, we came to the summary and the key takeaways. The Miller effect causes a small feedback capacitance to appear much greater at the input, reducing amplifier bandwidth. Every RC node in a circuit introduces a pole, and the dominant pole largely determines frequency response. Pole splitting and Miller compensation are widely used to improve amplifier stability. Noise sources such as thermal noise, short noise, and flicker noise affect amplifier performance and must be carefully managed. A strong understanding of these concepts is essential for designing stable, high-speed and low-noise amplifiers for analog and RF applications. Thank you for attention. Thank you. We hope you all understood. We'll see in the next lecture video.